Assalamualaikum. In this video, we'll continue discussing the principles of counting. And after permutations, we are going to learn about the combinations in this lesson. Just like permutations, combination is the way of selecting R items from N with this additional relaxation of the constraint that the order of items in the arrangement does not matter. While in contrast to combinations, with permutations, the order of item does matter. So if the position of an item is changed with another item in the same arrangement, it is going to make a new instance of the new permutation. But in case of combination, the only thing important is composition, which items are there in the selection and not how they appear, in which order they appear in the selection. So basically, we're talking about taking a sample from a pool of items, from a collection of items, and we're doing that without replacement. So the combinations are going to tell us the expression for this. They're going to tell us how many different distinct combinations can be formed if R items are to be selected from N. And this is how it is done. So this is how you would write it. And it's normally said as R choose N, which is that you're choosing R items from N, a pool of N items. And this is how you calculate it. This is N factorial, which is the total number of items in your pool, divided by N minus R factorial into R factorial. And so you see here, the difference from permutation is that you have this additional term, which is the R factorial in the denominator. And now you can well understand that the number of combinations is going to be smaller than the number of permutations for the same value of N and R. And it is logical also, because since the changing the order of an item, if it's changed, it does not create a new instance of a combination, but it does make a new instance in case of permutation. So the number of permutations for the same configurations of R and N are going to be much larger than that of the combinations for the same settings. Consider an example. So if we are to choose a 3 members team for a quiz competition from a class of 20 students, and if you're asked to determine the total number of distinct compositions of team that are possible from those 20 students, this is clearly a matter of selecting our items where the order does not matter. So we're going to use the expression for combinations to find this out. And you can write combinations using this format as well. You may write it this way or this way. So this again is that we're choosing from 20 items, we're choosing 3 items, but the order of item is not important. And this is how we calculate it. And we get to know that it is going to be 1,140 distinct team compositions that can be formed using when we have to choose 3 members from a class of 20 students. Consider another example. In how many ways can you choose 5 out of 10 friends to invite to a dinner party? Now, from at this point onwards, we'll see many questions. But in every question, you'll have to, before you proceed to the solution, you first need to ask yourself whether the arrangements that we're talking about, the sample that we're picking from the pool, does arrangement, the order of items, does it make any difference? If it is important, then you will end up using the expression for the permutations, because what you form is basically a permutation. But if the order is not important, then it is a combination. So in this case, we are to choose 5 friends out of 10, and we just have to invite them to the to this dinner party. Clearly, it doesn't matter which order you send those invitations out to your friends. It's only the thing important here only is which of those 5, which from those 10 friends you are going to invite. So since the composition is important and not the order in which it is made, it's going to be a combination. And this is how we solve it. So we have to choose 5 items from 10. We use this expression and we get 252 different ways that you can call your friends, invite your friends to this party. So 252 different compositions for your dinner party. Now, the next question is, how many ways can you arrange 10 books on a bookshelf that has space for only 5 books? Now, again, we see that the pool is of 10 items. Here, those are books, and we have to arrange them. And we have to take 5 out of the 10 books at a time. Now, again, we need to ask ourselves, does it the arrangement make a permutation or a combination? So consider this, that you have a book on Java and a book on C++, and there are, of course, other books. But if you put the Java book first and then the C++ book, or if you put C++ first and Java later, it makes a different it makes a different sequence. Whatever you see on the shelf, it is different when you place one book uh, on the left or the same book on the right. So this is a question of permutation. We are basically making permutation. Every time you switch the position of a book, you get a new arrangement. You get a new sequence. So this is permutation, and we're going to solve it that way, which is now we have the same configuration. We have same 10 items. The number of items is 10, and we have to choose 5. The sample that we pick is 5 items. But this time, we get a much larger number of different arrangements possible, which is 30,240. And if you compare it with the question above, you see that the number of permutations for the same values of n and r is much larger as compared to the combinations for the same values of n and r. Another example, it says that a voicemail system password is one letter followed by a 3-digit number less than 600. How many different voicemail passwords are possible? So let's take a while to understand this question before we proceed towards the solution. We have to find out the total number of different arrangements that are possible with this structure, which is given. It's a 4 letters password. The first one is a letter, which of course means that it's going to be a very fixed number of different values which are possible over here. And then it is a 3 digits number, and it also has a constraint. So whenever there is a question which involves finding out the total number of different arrangements which are possible with a given structure, or from when you collect it, when you pull a sample from a collection, not every time it is going to be a combination or a permutation question. It could sometimes involve some basic rules or laws of counting that we've studied earlier. So this is one of those examples. So for the first letter, since it is going for the first place, since it's going to be a letter, it can be 26 of the small case letters and 26 of the uppercase letters. So a total of 52 possible options for the first place. For the second place, it is a digit, but there is an additional constraint that it cannot be, the total number, the 3-digit number cannot be greater than 600. So we cannot, of course, restrict the other two places after this digit to be zeros. So what we can do here is that we only allow values from 0 to 5 to ensure that the number doesn't go above 600. So it's not even equal to 600. So we cannot have 6 at this place. So this means that for the second position, which is the first of the 3 digits number, it's going to be only 6 different possible options from 0 to 5 that can be filled, that this space can be filled in with. The second digit in the 3 digits number, which is basically the third place in this password, it's going to be from 0 to 9. It can take any value from 0 to 9, making a total of 10 possible options for this place, and another 10 possible options for the last place. So this is what we have here. 52 options for the first place, 6 for the second, 10 for the third, and 10 for the fourth places. And the total number of variations by using the basic laws of counting, we get it as 52 into 6 into 10 into 10, which is 33,600 different voicemail passwords that you can make, which comply to this constraints or the structure that is given. Here is another example. It says that a group of 8 swimmers are swimming in a race. Prizes are given for the first, second, and third places. How many different outcomes are there? So now again, we need to first understand and find out if it is to be solved using the permutation expression or the combination. Does the order of the arrangement of items that we pick from the pool, does it matter or not? So since the items that we pick, they have they have some kind of ranking or ordinal structure. So we know that if we change position, it is going to make a different arrangement, a new instance of the arrangement. So this is clearly a permutation which will be made when we pick one group of three items from these 8 swimmers. And if we change the order, it is going to be a different group. It's going to be a different arrangement. So we solve it using the permutation expression, and we get it as 336 different ways that three winners can be selected from this group of 8 people. Consider this example here. In a batch of 20 electronic files, 5 are infected with malware. A program randomly picks 4 files for scanning. What is the probability that all infected files get scanned or they got picked? So here we need to find out the probability. And earlier we have been doing combinations. So you must be wondering what is the connection between the combinations and permutations that we just did, and how do we relate it to the finding probabilities. And this is what's known as combinatorial probability. Before proceeding to the solution, it's better we recall how we can assign probabilities to events. Here, the event of interest is that we pick a set of 4 files from this group of 20, and all of those files are infected ones. So by our early discussion on how probabilities are assigned to events, we know that there are 3 ways that we can do it. The first one is classical approach, where all possible outcomes of an experiment are known, determined, and each one is assumed to be having equally likely probability of occurrence. And then all the occurrences of the interest, they are added up, and the probabilities basically they're added up, and they're divided by the total number of outcomes possible. So this is the classical approach. The second one is empirical approach, in which we use the relative frequency approach and run an experiment multiple times and note the number of successes. And we use the relative frequency of successes against the total number of experiments to assign the probability. And the third one is subjective. In this case, the combinatorial probability, it works with the classical method. So what we do is we find out all possible combinations of outcomes which are possible for a given arrangement. And then among those, we find out the number of arrangements that correspond to the event of interest. And by dividing this count of arrangements carrying the fulfilling the said criteria by the total number of outcomes, we find the probability of the given event. So here, first we need to extract the data from this question. There are 20 files we know. 5 of them are infected. So this basically makes 2 subgroups within this collection. One is a subgroup of 5 items which have a certain characteristic, which in this case is that they are infected. And then there is a subgroup of 15 files which are not infected. And we have to choose 4 files, or basically that we're picking up a sample of 4 files from this pool or this population. And whenever we are doing it this way, it's basically sampling without replacement. So we pick a sample of 4 from a population of 20 files. And at this moment, irrespective of whether the files are infected or not. And we find out the total number of combinations, the total number of different compositions of 4 items selected from 20, which are possible. And we use the combination expression for that. We get the value as 4,845 different compositions. So 4,845 different ways, different groups of files, 4 files can be selected from 20. Again, at this moment, irrespective of whether they were infected or not. Now we do the calculation with the number of combinations which correspond to the event of interest, which in this case is that all of the chosen files were infected. So for this, we consider the 2 subgroups that we have formed in this pool. We know that there are 5 files which are infected, leaving 15 other files which are not infected. And we have to choose a total of 4 files. And the question wants us to find out the probability, or at this moment, we're interested in those combinations which involve all of those 4 files picked up from the infected files subgroup. So here, we calculate the number of combinations of files, 4 files picked from the subgroup of 5 files which are infected, which leaves none of the files to be chosen from the other subgroup of not infected files. And we take the product. Because for every file selected here, every group of files selected here, there's going to be this number of group of files selected from the other subgroup. But in this case, coincidentally, we do not have anything being chosen from the other subgroup. And by definition, 15, this is going to be 0. Choosing 0 items from any number of items is going to be 0 by definition. So here we have this value comes out to be 5, and this comes out to be 1 by definition, and by this product is 5. So we have 5 such combinations which involve all 4 files which are infected. And the total number of combinations for 4 files, irrespective of whether they're infected or not, or any composition of them, 1 may be infected, 2, 3, or 4, any irrespective of whatever the infection status of the file, you have a total of 4,845 such combinations. So we calculate the probability using the classical approach, the count of events of interest, which is the observation of interest, which is 5, divided by the total number of outcomes, which is this, and whatever the value of this is the probability of this event. Consider another example here. It says that 5 students are selected from a class of 17 and given some responsibilities for the preparation of an event. Later, the class teacher selected a group of 8 students from this class for another assignment. What is the probability that the selected students contain 3 students who already had the responsibilities? The 5 students who had responsibilities, so 3 of them get selected. Now, before proceeding to the solution, let's take a while to understand this question and find out what it demands. From a very quick look, we understand that we need to find out the probability of a certain event. And the event is that a group of 8 people are selected from 17. Basically, that we take a sample of 8 from a pool of 17. And the sample should have a certain characteristic, which is that it should have 3 items with certain characteristics. In this case, it is in a class of 17, 5 students are the ones who had responsibilities earlier, already given some responsibilities were assigned to them. And this leaves that 12 students did not have any responsibility. But then a group of 8 people are selected from this 17 students, including both the ones with responsibilities, the ones who did not have responsibility. And now the event that we're interested in is that these 8 people contain 3 students who already have responsibilities, which means 5 are the ones who do not have responsibility, but 3 are those who have responsibilities. And we know that there are 5 such students who already had responsibilities. Now we have to find out the probability of this event. Now, if we recall how we can assign probabilities to events, we know that there are 3 ways that we can do it. The first one is classical method, in which we consider that any outcome is equally likely. All possible outcomes, they are equally likely. And then we find out the frequency of the outcome of interest, and we divide it by the total number of possible outcomes. Then there's the empirical approach, in which we repeat the experiment multiple times, n times, and using the relative frequency approach, we assign the probabilities. And the third one is subjective probability. In this case, we're going to use the classical approach, because what we do is, if we consider it on as a very basic formulation, it is that we have from a pool of 17 items, we pick a sample of 8. And those it can have, every time we pick a sample, it can have a different composition. So first we identify the total number of different compositions that we can pick from this pool of 17 items, 8 items from this pool. And this is equivalent to that we're doing a sampling without replacement. So we're picking 8 items, from the pool randomly. So first we do is we find out the total number of combinations or arrangements that are possible, or total number of samples that are possible when 8 items are picked together. And after that, we find out the arrangements which contain the which fulfill the given criteria, which contain the event of interest, which in this case is that 3 of those items need to be from this certain subgroup, which is 5 items. So here is how we solve it. Let's define this event A. to be the event that 3 students with responsibilities are chosen among the group of 8 selected students. We know that the total number of students are 17. 5 of them are the ones who possess the given the desired characteristic, which is that they have responsibilities already, which means 12 are the ones who do not have any responsibilities. And we have to choose 8 students. At this moment, irrespective of whether they have responsibilities or not, it's from the total pool of 17 students, including both types. So the total number of different samples that are possible, the total number of different 8 members teams that is possible to be selected from these 17 students is given by this combination expression, which is 24,310 different combinations. 24,310 different team compositions. Now, we are interested in those events, those arrangements which contain 3 such students who have responsibilities already. Here we know that there's a small group, 5 students, a subgroup from this the 17 students who have this desired property, desired characteristic of having the responsibilities already given to them. So this leaves 12 other students who did not have responsibilities. So we have 2 subgroups in our this pool of 17 students. 5 are the ones which possess the desired characteristics and 12 who do not have that. And we have to choose 8 students. Now, the event is that 3 of them should come from the subgroup of interest, which is 5 students, which means that the remaining, if from 8 we subtract 3, we get 5. So 5 students should be selected from the other subgroup. And this is how we calculate it. Here we have C, the combination when we pick 3 students from 5. These are the ones which correspond to the event A. And since the total number of students selected should be 8, we need to complement it with 5 students being selected from the other subgroup, which is 12 students who did not have the responsibility. So first we calculate this thing, which is 5 factorial over 5 minus 3 factorial into 3 factorial. And then we can calculate this, which is again this. So we have 10 from this first combination and 792 from this second combination. And for every arrangement of the first combination, we have these many possible arrangements for the second selection from the second subgroup. So we multiply them together to get 7,920 such arrangements of 8 students which have 3 such students who already had been given the responsibilities. And now to calculate the probabilities, we need to have follow the classical way, which is number of combinations of interest divided by the total number of combinations, and we get it as 7,920, which is the combinations of interest which fulfill the criteria asked, and 24,310, which is the total number of combinations with 8 students. It gives us 3.3258, which is 32.58% chance that if 8 members committee or group is selected from 17 students, it can have 3 members from the other group which had responsibilities already given to them. Let's consider another example so that we understand the concept better. It says that 15 candidates applied for a job that needs skills in Java programming. 5 of the candidates did not know Java. Now, an assistant randomly picks 4 CVs and calls the individuals for interview. What is the probability that at least 3 of the called people did not know Java? Now, clearly, we need to find out the probability of an event, and the event says that among the 4 CVs that were picked randomly, or a sample of size 4 that was taken from this pool of 15 items, at least 3 of them possessed a certain characteristic. Now, if we take a closer look at the question, we know that, and this is, by the way, it's going to be whenever there's a question of probability, you need to take a while first to understand the question and what it asks and what facts are given and how, of the 3 possible ways that we know of assigning probabilities, which of those are you going to use? Most of the questions, they're very straightforward. They're very clear from the statement, and you can always find out what they're referring to. The types of problems that we're solving at this moment are basically combinatorial probability because we're using the combinations to find out the probability. And it is done using the classical approach as we've already discussed. So here we know that there is a pool of 15 items, in this case, which are 15 candidates. There's a subgroup in this, which is 5 people who do not know Java, which means there are 10 people who know Java. So there are basically 2 subgroups, 5 having this characteristic of not knowing Java and 10 who know Java. Now, the selection or the sample is size 4. So we pick a sample of size 4 from this, and it's done randomly. Now we need to find out the probability that the sample that we pick has this characteristic, or it conforms to the event that at least 3 of the chosen series were belong to people who did not know Java, which means that there could be 3 people with, since it is at least 3, it means that there could be 3 people who did not know Java or 4 people who did not know Java. Although we have a total of 5 such people, but since we are making a selection of only 4 people, so the event here is either 3 people, they do not know Java, or all 4 of them, they did not know Java. So how are we going to solve it? First, we need to extract the data from this question. And so we need to find out the total number of combinations which are possible with when we have to select 4 from 15 items, 15 of these candidates, irrespective of whether they need Java or not. Any 4 people from this group. So it's going to be, we choose 4 from 15, we get this value, which is 1,365. Of course, we're using the same expression for the combination, which is n factorial divided by n factorial, n minus r factorial into r factorial. You can recall the expression by going back. Then the required event is, we're interested in knowing the number of combinations which involve people, either 3 of such people who did not know Java, or 4, all 4 of them, the ones who did not know Java. Because it says that it should be at least 3, which is 3 or more. So this means we are going to find out number of 2 different kinds of arrangements. The first one is the combinations with 3 people who did not know Java. And since we're choosing a total of 4, this needs us to find this combination, which is 3 from the subgroup of 5 people who did not know Java, which is the event of interest. And this leaves us with 1 person to be chosen from the other subgroup of 10 people who knew Java, because we have to make a selection of total 4 items. So here we have 3 being chosen from this subgroup of 5 non-Java people, and 1 from the other subgroup of people knowing Java, to make a total of 4 people being selected. And here it is, 10 from this and 10 from this. You can do the calculations to verify this. So we have a total of 100 such combinations which have 3 people who did not know Java. Of course, then 1 who knew it. And since we have to find out the probability of 3 or more, we also go for the combinations with all 4 of them not knowing Java. So here it is going to be choosing 4 from these 5 people, which means since all 4 of them are selected from this subgroup, we do not need to select any from the other subgroup. And so here's a 0 here. And by definition, this is a 1. So we have 5 into 1. 5 is the calculation outcome from this. So we have a total of 5 such combinations. Now, the total number of combinations having either 3 or 4 people not knowing Java is 105. And this is basically the event of interest. And now we find out the probability by using the classical approach. And it is 105, the number of outcomes of interest divided by the total number of outcomes, which is 1365. And we get it as 0.077, or a 7.7% chance that this will happen. That at least 3 of them would not be knowing Java. Here's another example. Ali has a box of chocolates having 3 mint flavored, 4 strawberry, and 2 orange flavored chocolates. What is the probability that if he picks 2 chocolates from the box, both of them are the same flavor? Now, this question, again, first, I emphasize this and I keep on saying this again and again, that with probability, you need to take a while to understand the situation, the scenario given to you, and then decide which approach you're going to follow to find the solution. So here we are given a scenario that there's a box of chocolates with 3 different flavors, mint, strawberry, and orange, and each of the different number of items in each of these subgroups. So there are basically 3 subgroups: mint, strawberry, and orange. We have 3 items from the mint subgroup. We have 4 items from the strawberry subgroup and 2 from the orange subgroup. Now, the selection is, or a sample taken is size 2. So we choose 2 items from this randomly, which could be any flavor. But the event that we're interested in is that both of them have the same flavor, which means if it's mint, both of them are mint. If it is a strawberry, both of them are strawberry. If it is orange, both of them are orange. So now from this discussion, you already must have learned that it's going to be a calculation of 3 different probabilities, and it could be either of those. The event would be satisfied. The event would happen if you choose 2 mint, it is going to happen if you choose 2 orange or if you choose 2 strawberries. So it is basically that we need to find the probabilities of 3 of these events and combine them, add them together to find the overall probability of this event that any of these flavors, we get a pair of chocolates from any of these flavors. So how do we do? So the first thing we need to do is we find out the total number of combinations which is possible, irrespective of which flavor we are choosing from this box of how many? We have a total of 3 plus 4, 7 plus 2, 9 chocolates. So we are choosing 2 of them. So this is how we calculate it. We have 2 from 9 and we get a total of 36 different ways that we can choose 2 chocolates from this. So now we find out the combinations having both of them being the mint flavored chocolates. This is going to be very easy because we know that there are a total of 3 mint flavored candies here, and we choose 2 from them, leaving none from the other group, from the rest of the chocolates, which are 6, because we have a total of 9. So the first step, since we are dealing with the event of having 2 mint flavored, so we have 2 subgroups here, the ones having the mint flavor and the others not having mint, irrespective of whether they have strawberry or orange, but they're not mint. So we have 3 such candies here, and we choose 2 from them. And since we have to choose only 2 from the entire box, we do not choose any from the rest of the flavors, whatever they may be. So we have 2 from 3 and 0 from the remaining 6. And this gives us 3 into 1. By definition, this is 0. This is 1. So we have 3 such combinations. Then we need to find a number of combinations with when both of the selected candies are strawberry. We know that there are a total of 4 strawberry flavored chocolates. So we choose 2 from those and we choose none from the remaining. And the remaining, when we take 4 strawberry flavored out, the remaining are 5, irrespective of whatever flavor they may be. So we choose 0 from them, and we have, again, by definition, this is 1, and from here we get 6, so this is a total of 6. Then we have the number of combinations with both orange flavored candies. So we know that there are only 2 such chocolates having orange flavor, so we pick both of them, leaving none to be picked from the rest of the 7, irrespective of whatever flavor they may be. So that there's a 1 into 1, and we get a 1. So a total number of different arrangements involving 2 same flavored chocolates are 3 from here, 6 from here, and 1 from here, which makes a total of 10. So now we have the total count of same flavored chocolate arrangements is 10, and the probability of having the same flavor is 10, which is the frequency of the outcome of interest divided by the total number of possible outcomes. This gives us 10 by 36, which is 0.275, or 27.8% chance that those 2 candies picked randomly out have the same flavor. Okay, now this is the same question that we did in one of the earlier lessons, precisely in the conditional probability lesson. And we're going to do it using the combinatorial probability here. So Ali has 25 pens on his shelf, 4 of which are defective. He randomly takes 2 to the exam hall. What is the probability that he gets the shocker slide, which means that both of those pens were defective, they do not work. Earlier, we did it using the conditional probability. Now we're going to use it in a much simpler way using the combinatorial probability. Here we know that this is a group of 25 items having two subgroups, which is 4 being defective and 21 being not the working ones. And we choose 2 from this pool. The probability that we need to find out is of the weight that both of those selected pens are from the group which were defective. So first we find out the total number of combinations which are possible with when we choose 2 items from a group of 25 and we get it as 300. Then we find out the number of combinations with 2 defective ones. So again, we have 2 subgroups here, 4 which are defective, 21 which are not effective. We choose 2 and the total number of items to be chosen are again 2. So 2 from the defective category, leaving none from the working category. So we have 2 from 4, but none from 21, and this gives us 6 into 1, which is 6. Now, there is the total number of combinations involving both of the pens being defective is 6, and we find the probability very easily by using the classical approach. This is the outcomes of interest, and this is the total number of possible outcomes, and we get it as 0.02, which is the same as what we got when we computed it using the conditional probability.